This is going to be in the spirit of the first talk of the morning session by Professor Silva, so it's going to be rather theoretical, and there will be few connections with superconducting devices that I hope might be anyway of interest. So this is the group that is responsible for this research. That's me and my collaborators, Alfonso Maielaro and Antonio Marino, and then this work has been done in collaboration also with Roberta, Francesco Romeo, and currently also with people in Japan. Okay, today I'm talking about how to benchmark and build figures of merit for quantum technology devices based on subsystem entanglement. This is the basic notion I want to introduce today, and I want to be specific about that. And by subsystem entanglement, I mean any measure of entanglement that has the capability of going beyond von Neumann entropy and block entropy. So if you're familiar with von Neumann entropy, block entropy, basically you bipartite a many-body system, for instance, in two halves, in two parts, and then you trace out one of the two parts and you construct the von Neumann entropy of the reduced state. And that is a measure of the entanglement between the two parts. But essentially, this works only for pure states. And moreover, it's limited by the fact that you have to consider exactly two parts of the system without accessing details on the subsystem dynamics, essentially between different parts of the system that can be of interest. Now here I'm thinking about a specific example, but you can figure out many others. For instance, a system in which it is very important to compute the entanglement, assess the entanglement, qualify the entanglement between the edges, for instance, or between the bulk and the edges, and not between two parts. Okay. Why is this important? Because in the passive approach to fault-tolerant quantum technologies, what you are trying to obtain is to have devices that support phases that are intrinsically robust against the coherence and noise effects. And topological phases are one prominent example of this possibility. Now, topological technologies, and based, for instance, on superconducting, on topological superconductivity, but not restricted only or limited only to topological superconductivity, have the potentiality to provide devices in different fields of quantum technology, including sensing, including metrology, and possibly, of course, the holy grail of topological quantum computation that I will, of course, not talk about today. So this is just a list of few examples in which the physics of the edges, so the presence of robust entangled edge states, can be exploited for technological purposes. Now, after this very brief introduction to the potentialities of topological phases of matter in quantum technology, let me discuss about what quantum information tools can teach us about these potential devices for quantum technologies. Here, the crucial ingredient is the long-distance entanglement between the edges of the system. And this kind of entanglement can benchmark a topological device and discriminate it with respect to different types of quantum devices based on spontaneous symmetry breaking and different phases of matter that are based on more common phenomena, which parallel classical phase transitions. So typically, when you think of a phase transition in a material, you think about a phase transition that involves local order parameters and the spontaneous breaking of a global symmetry of the system. Paramount example is, of course, ferromagnetism, but there are many more. Now, this is a very classical concept that is translated also in the quantum domain. Topological phase transitions work in a completely different way. There is no symmetry broken. and there is no local order parameter. So actually the non-locality of the ground state of these systems is exploited, or is actually witnessed by the presence of this highly non-trivial entanglement between separate parts of the systems. And this is where this idea of going beyond block entropy, von Neumann entropy, sets in. And it is well known that von Neumann entropy, block entropy, is not able to discriminate between spontaneous symmetry breaking and topological phases of matter. You look at the entanglement spectrum of an Ising chain, you look at the entanglement spectrum of a Kitaev chain, and they're exactly the same. So you have to go beyond that. And this is an ongoing quest that has been going on for at least 10 years now, more. And now it's more or less clear how one has to proceed to qualify, quantify, and discriminate topological phases from symmetry breaking phases using different measures of entanglement, different concepts of entanglement theory with respect to von Neumann entropy. Now, as I said, the traditional tool, how you characterize quantum phase transitions in the traditional domain of spontaneous related to spontaneous symmetry breaking, were typically by correlation functions, endpoint correlation functions, and local order parameters. Now, the modern approach has been to characterize them with entanglement, and in particular with bipartite entanglement. So you have the two halves of the system. In case of a product state, you trace out one of the two subsystems, and what is left is a pure state, and then you know the system is not entangled and there is nothing important happening because no local correlations are suppressed. While in the case of a non-product state, of course here I'm limiting myself to the case of pure states, you find out that upon tracing out one of the parts of the systems, what is left is in a mixed state, and this signals the presence of entanglement. You're losing information. This is well known, of course, from entanglement theory. You're losing information, and the best way to quantify it is by an entropy, so by an extensive quantity. But this is not the end of the story, because this block entanglement entropy obeys an area law. And when this area law is actually, so a boundary law would be the correct naming, but by now the popular way is area law, but of course it could be a boundary, so it could be, strictly speaking, it's an area only when you are 3D. It's actually a perimeter when you're in 2D. And it's the edges when you are in 1D. The edges at the frontier between the two blocks, the two parts of the system. Now, the important result of entanglement theory in many body systems is that this object obeys an area law. So it scales as the system size grows, it scales with the boundary of the system, the dimension of the boundary of the system. And this is not true when you go to criticality. Then this is violated, and this is the signal of a quantum phase transition. Therefore, you have, when you are in the ordered phase, therefore you have a very simple and efficient tool to understand quantum critical phenomena. But this simple and efficient tool fails in two important domains. First of all, when you are considering situations, for instance, at thermal equilibrium or in non-equilibrium dynamics, which are extremely important and extremely general in physics, in which you have to deal with mixed states, because the von Neumann entropy of a mixed state is not an entanglement measure, of course. It measures the total correlations. Everything is mixed. Thermal contributions plus quantum ones, and the entropy in that case is not able to discriminate between the different contributions, quantum and classical. The second instance is when you have to do with symmetric states, so states that do not break any symmetry of the system or the relevant symmetries of the system. And in this case, there is no evident possibility to discriminate these states that do not break symmetries with states that do break the symmetry using the von Neumann entropy. So it has some scopes, but it has also some limits. And we have to go beyond that if you want to discuss, for instance, the physics of topological insulators and topological superconductors. also because if we want to use these systems for quantum technology applications, we need to benchmark them and know when the figure of merit is high enough, large enough to provide an efficient device, and then we have to know what is the best working point in the quantum phase diagram. And to know that, we need to have a faithful non-local order parameter able to characterize the system. How do we proceed? Okay, this is something I've already mentioned at length, so we can skip this. It was just a resume of what I've been saying so far. We have to look at the full structure of many-body entanglement. This is the, and Alessandro Silva has already talked about that, has mentioned that in a very interesting, for the very interesting case of understanding black hole physics, which is very complicated. I would like to mention in that respect also the Firewall Paradox, the breaking of monogamy of entanglement, and many interesting features that tell us that clearly, block entropy, von Neumann entropy is not the end of the story, it's the beginning of the story, actually. That's, there is much more uncharted territory left to explore, and we are just beginning to explore this territory. And Professor Silva's talk was a nice example of that. Now, of course, one would like to characterize the full entanglement of a many-body system using a hierarchy of fully multipartite entangled states. One way to do that is to witness it by the Fisher information, but you would like to have also a finer description, a finer understanding, a much deeper understanding, and this is very hard to achieve because multipartite entanglement is very hard to characterize, to qualify, and to quantify. So things are still ongoing, and I would say that this is the least developed branch of quantum information and quantum entanglement theory, and there is still much work to do there. At the fundamental level, before we can start using this, applying this tool efficiently to the detailed study of quantum many-body physics. Next, well, I skipped the blue line. I'll come to that as the last one. Then we have the block entanglement entropy. We have seen this is very useful but limited. Then we, in the beginning, if you remember the paper by Sarofazzi and others, 2000 in Nature, the concurrence, they studied the concurrence in the quantum spin chain. In the quantum missing chain, there was just the spin-spin entanglement just between two sides. At that time, it was a big deal, right? But now, of course, this is an historical relic, and it's really, you always can express it in terms of two-point correlations, so it's not extremely interesting, actually. But at that time, it was extremely useful to convince people to study entanglement in the realm of many-body physics, so we have to pay tribute to the historical relevance of this contribution. And then, unfortunately, in the quantum many-body community in the last years, there has been a plague going on, which is the entanglement negativity. And everybody uses it because it's extremely simple to compute. And people draw very general conclusions about the dynamics and the statics of quantum many-body systems using the negativity, which is defined on all states, also mixed, so that does not have the problem of the von Neumann entropy of not being well defined as an entanglement measure for mixed states, so that's okay. But has many, many drawbacks that lead us to conclude that actually it's a very ill-defined measure of entanglement, should be avoided like the plague, like a pest. So what we are, and I will show you why in a short while. So what I would like to actually concentrate in the remainder of my talk is about how to construct faithful measures of bipartite entanglement between subsystems. This is not yet at the level of multipartite entanglement, but starts to get close to that idea, because to construct these faithful entanglement measures between any pair of subsystems in a many-body system, you need multi-partitions. So block entropy is bipartite-based, is a bipartite measure of entanglement based on bipartitions. Now we'll show you a very useful and important example of a bipartite measure of entanglement based on multi-partitions. And I'll show you how it works, what is the idea. So this is block entanglement, two halves of the systems, A and B. I trace out B, for example. I construct the von Neumann entropy of A, and then this is the entanglement between A, measures the entanglement between A and B. Now, how does it work when I have, for instance, let's make it the minimal case, a tripartition, A, B, C. So why I do like this? Because I'm already thinking about a topological chain where A and B are the edges and C is the bulk. Okay, but this is very general, of course. The topological chain is just one possible example. And then the idea is I trace out C, and I need to construct a measure that tells me how much entanglement there is between A and B, or I trace out B, and then I need to have a construction that allows me to build a measure that measures, a quantity that measures the entanglement between A and C, and so on and so on. Okay. This is the idea. Does such a measure exist? Yes, of course, the answer is yes. It's well known since some years. It's the so-called squashed entanglement, because the construction squashes out the classical correlations from the different entropies, and what is left in this linear combination of reduced von Neumann entropies is a quantity of purely quantum nature. Okay, this is the idea. Now, the squashed entanglement has a nice story. It was introduced by a guy who never publishes on journals, but only on archive, Mr. Tucci. So if you go there, you see this long list of archive papers never published in any paper because he refuses the system of institutionalized journals. He's an American, and working somewhere, I don't know where. And then Andreas Winter, who is a well-known mathematical physicist now in Barcelona, decided it was about time to publish. And so they put it nicely in Journal of Mathematical Physics about 20 years ago and called it squashed entanglement. The squashed entanglement is built on another quantity, which is called the quantum conditional mutual information. And the quantum conditional mutual information between A and B. So you remember the tripartition ABC I showed you before. And the mutual information between A and B, conditioned by part C, is this apparently complicated combination of reduced von Neumann entropies. But actually, the meaning is rather clear. I have the sum of two von Neumann entropies between blocks A and C and blocks B and C. So the correlations between A and C and B and C. And then what I do? I subtract, first of all, what is the entanglement of C with respect to A and B, and then the overall entropy measuring the total fluctuations, the total statistical fluctuations in the total system ABC. And what is left is this purely quantum quantity. This is not yet an entanglement, because, of course, rho ABC could be anything, could be any state. Then you take the infimum over all possible states of this tripartition, and this is what we call squashed entanglement. This is how you build this entanglement measure. Okay? By squashing out all the remaining correlations, taking the infimum. So this is, of course, an optimization procedure that is very complex and makes it hard to compute this quantity, of course. You pay a price for this definition. The nice thing about squashed entanglement is that it fulfills all the axiomatic requirements for a good measure of entanglement. No other measure fulfills at the same time all these quantities, all these requirements, sorry. Faithful means that the entanglement is zero if and only if the state is separable. Now, for instance, the negativity does not fulfill this. You see, you think, okay, this is a fundamental requirement, right? This has to be zero if and only if the state is separable. Well, for instance, the negativity does not fulfill this. We know that there are states for which the negativity is zero, vanishes, but these states are entangled. It's called the bound entanglement because it cannot be distilled by local operations. Okay, continuous. If two states are very close in Hilbert space, I expect that their entanglement is very close. Very few measures are continuous, and the negativity is not, for instance. Additive on tensor products. This everybody understands about an extensive quantity. Extensive quantities have to be additive, like an entropy. if I have a tensor product of two entangled states, then the total entanglement must be the sum of the two separate entanglements, exactly like the standard entropy in thermodynamics. If it's a sub-additive or super-additive, not that great. Eh? And indeed, the negativity is not additive, for instance. Convex, so when I make a linear combination of states, the resulting entanglement must be less than the convex combination of the two constituting entanglements. Monogamous. Monogamy, Alessandro didn't talk about monogamy, but he touched it somehow upon it. And monogamy is also a very interesting property of entanglement, in which monogamy tells you that if A and B are maximally entanglement between each other, then neither A nor B can be maximally entanglement with C, with a third party, okay? Monogamy in the sense, okay, that they stick together somehow. Many measures are monogamous, including squash, and guess what? The negativity is not monogamous. And finally, F is also extremely important. What is the measure we use for entanglement on pure states? Always von Neumann entropy, because it's so obvious that it's the right measure. And it's called a unique entanglement measure for pure states. Many measures do reduce to the von Neumann entropy on pure states, including the squash entanglement. The negativity, again, no. Okay. Yes?
Could you explain again, why would we redivide the system? Why isn't there a well-defined A and B? Why is there an infimum definition?
In the previous slide?
Yeah.
Yeah, you see, when you have something like this, some quantity like this, if you want to have the entanglement between A and B, you have to take the infimum over rho ABC, because rho ABC can be obtained by any tracing. And now you have many different ways of defining these density matrices. Actually, you have infinite. This is the Schrodinger Theorem, in which you know that you have infinite ways of describing the same state by different density matrices. And therefore, you have to take the infimum, which, of course, tells you that it's very hard to compute the measure. Thank God we have bounds. And the first bound is, of course, given by I. By the quantum, this is automatically an upper bound. Now, if you're able to find also lower bounds, and these are strict enough, even if you can't compute the exact squashed entanglement, you have like two soldiers from the above and from below, and following them, you know more or less.
So if rho ABC happens to be a pure state, then...
Oh, then this is zero.
Then you're good.
Yeah. And then you reduce to von Neumann. And you see why. Because this guy is zero, these two are the same, are equal, and 1/2, 2, and it gets exactly the von Neumann entropy, okay, on pure states. So this is easy to see. And this, if it's pure, this is product, so the rho C contribution factorize out. So what I wanted to say is that all these quantities are satisfied by either measure, like, I don't know, entanglement of formation, and other possible measures, but only one measure, the squashed entanglement, satisfies them all. And the negativity doesn't satisfy almost nothing of this, okay, although it's the most used. Well, because it's easy to compute again. Now, I show you a three-partition, but actually, as I mentioned you, ABC could be a mixed state, rho ABC. Yeah, okay, wow. So I'm not even halfway through. Okay, so anyway, you have two independent ways of defining the squashed entanglement, by a three-partition or by a four-partition, and when you take the infimum, these two quantities coincide. And this means that you can either trace out the bulk completely or trace it out partially. This makes a strong difference when the bulks, if the bulk is insulating, then this doesn't make any difference. I3 will be equal to I4, but if the bulk is conducting, this makes a difference. And this allows to use the squash entanglement to discriminate between spontaneous symmetry breaking and topological phases. And so this is exactly what we have done, comparing the Ising chain with the SSH insulator, topological insulator with the time reversal symmetry, and the Kitaev superconductor with particle hole symmetry and P-wave superconductivity. And you know that the SSH is defined on unit cells with two different species of fermions for each unit cell, while the Kitaev chain is defined as one fermion per site with some chemical potential that we take to be uniform, but of course we can also consider the case of disorder and have non-uniform hopping or non-uniform offset energy. And our result, we compute the edge squashed entanglement between the edges of these two chains and compute the phase diagram for the SSH topological insulator and for the Kitaev topological superconductor. And we reconstruct the exact phase diagrams for both using the squash entanglement, which is very encouraging. Plus, we notice that the squashed entangle is able to discriminate between the two different types. These are two different types of physics, of course. Both bulks are insulating, but the symmetries are very different between the two models. And they belong to two different classes of the tenfold classification of topological phases. And what we find is that in the case of SSH, where the edge modes are fermionic, we have a 2-fermion edge-edge long-distance entanglement, which is logarithm of 2, the maximal Bell state entanglement. While for Kitaev chain, which is Majorana, has Majorana edges, so half a fermion in popular jargon, then the entanglement between the two edges is exactly half of the Bell state entanglement. This is the phase diagram measured as this ratio, I4, the quantum conditional mutual information, normalized by the Bell state entanglement. Okay. And so this is the summary of what we have found. That the squashed entanglement is the figure of merit of topological phases in one dimension. It measures faithfully the edge-to-edge long-distance entanglement, captures the essential physics of it, and discriminates between topological insulators and topological superconductors. And it works also when you have multiple phases. You see the superconducting ladders which have phase diagrams reminiscent of the quantum Hall effect, and they have multiple phases in the sense that they have phases with different number of edge modes, and these are again identified and discriminated by our edge-to-edge squashed entanglement. So it works also for ladders, and we hope to extend it soon to 2D as well, for models that do have, of course, edge states, which are called corner states in 2D, like the higher dimensional topological superconductors, but of course 2D is harder as long as numerical simulations are involved. It works also, it's very stable also against interactions, no time to show it, but in case in the question time I can show you. So it reproduces the consensus phase diagram also for interacting topological systems. When I say consensus phase diagram, I mean the phase diagram of the consensus phase diagram obtained by combining different numerical methods, including the MRG and other analytical numerical approximate techniques. And it's also robust against noise and imperfections, as a topological phase must be, of course. Like if you have local noise and local imperfections that do respect the symmetries, then you know that it's topological if it's stable against this noise. And indeed, this is the case also with the edge-to-edge squashed entanglement. And finally, the last thing I want to show you is that it discriminates with respect to symmetry breaking. This is our quantum conditional mutual information for the Ising chain, essentially 0 all along, while for the edge-to-edge, while instead it's, of course, different from 0 in the case of our Kitaev topological chain. So we finally have an instrument, a tool, to discriminate efficiently between symmetry breaking and topological physics, and this was something that people were looking for a long time. The negativity. So people do use the negativity in quantum many-body physics, so we had fun using the negativity as well and comparing it with the squashed entanglement. For the SSH, the negativity is still okay, although it gives strange numerical results, but the qualitative features of the phase diagram are more or less reproduced. And then when you move to the Kitaev superconductor, a total mess. It's widely off the mark. The negativity screws completely the phase diagram, the correct phase diagram. And this is a beautiful example of an unfaithful measure of entanglement at work. it tells you that the entanglement is zero, is actually zero, when it's not zero at all. And there is nothing wrong in it, in principle, because the negativity is only zero is only a sufficient condition, it's not necessary. We know the negativity is unfaithful. Okay, the experimental addressability, last point, very last point. How do you measure this edge-to-edge squashed entanglement? This is tough, of course. It's already tough to measure the von Neumann entropy in real experiments, so the squashed entropy is going to be even tougher. And a possible strategy is that we know, I don't have time to show it to you, but there are beautiful works by Elliot Lieb and by Eric Carlen, published when Lieb was well into his 80s. You know that this year Elliot Lieb finally got the Dirac medal of the ICTP. Thank God he's still alive to be a recipient of it. Elliot Lieb made an incredible number of extremely worthwhile contributions to any branch of physics, mathematical physics. And in the very recent years, he got interested in the squash entanglement, and together with Eric Carlen published a beautiful set of inequalities for squash entanglement that involve Renyi entropies. You know, the Renyi entropies are somehow the Zallis entropies the normalized Zallis entropies of the von Neumann entropy, measuring the spectrum of the density matrix to the alpha or the Q power, according to what you want to do. And they are relatively easy to measure in real experiment. And this has been done in the Greiner group in a landmark experiment a few years ago for bosonic systems. Then the idea is to adapt Greiner's strategy to fermionic systems for superconductors and topological insulators, and extract information on the Renyi entropies that bound the squashed entanglement. This is the basic idea. And as I mentioned, the possible extensions include higher dimensions, 2D, high dimensional topological superconductor, and the holy grail, finite T and non-equilibrium, because the great feature of squash entanglement, of course, is to be defined for all quantum states, including mixed states. So we finally have, in principle, a tool to study faithfully the fate of topological entanglement at finite temperature and in non-equilibrium. And one thing I wanted to mention is that there is ongoing work on the quantum information paradox in quantum black holes related to what Alessandro was telling us in the beginning. Thank you very much for the patience for this tour de force.